In this video, we will look at chapter 5.1, which is about the length and the dot product in Rn, the real numbers in any dimension, and we want to study. Our learning objectives are to find the length of a vector and find a unit vector, find the distance between two vectors, find the dot product and the angle between two vectors, determine orthogonality, and verify the Cauchy-Schwarz inequality, the triangle inequality, and the Pythagorean theorem. So that's a lot of verification. So we will be doing that over the course of several videos for chapter 5.1. And then we will see in SIPI how to use a matrix product to represent a dot product. So from the Pythagorean theorem, we know that the length, or what's known as the norm, of a vector v in R2 is represented as norm of v with these two lines on either side of v equals the square root of the first component v1 squared plus the second component v2 squared. You saw this in calculus when you were using the distance formula in 2 dimensions. And then also from the Pythagorean theorem in R3, we have this relationship for the length, or the norm, the square root of the distance in the first 2 components, v1 and v2 squared, which just simplifies when we add it to v3 squared and square root it all, it simplifies to be v1 squared plus v2 squared plus v3 squared, all square rooted. And you saw these distance formulas in calculus, so these should be. So here visuals in 2 dimensions. Our vector v here is component-wise v1 on the x-axis and v2 on the y-axis. So this is what we think of in 2 dimensions as a Pythagorean theorem. Vector v is a hypotenuse of the triangle. And then in 3 dimensions, we've got vector 1, vector 2, and vector 3 combining to make this 3D vector v here that goes from the origin to a point in 3 dimensions. We label that point as v1, v2, v3. Okay, so in Rn, we are going to define the length, or the norm, of v to be this formula in n dimensions. So the norm, which will be v with 2 bars on the side, equals the square root of the squares of each component through the nth component added together and then square rooted. So important things to notice, because we're squaring, everything is positive now. So even if you have a negative component, you're going to end up with positive results or 0 results if you've got 0 components when you square. So notice that the norm of v is always 0 or positive. And the only situation we're going to get 0 for the norm is if each component of v equals 0. So that's saying v is the 0 vector with 0 in each of the n components. Okay, let's take a look at an example. So here we're going to find the length of this vector v in R4. So I can't draw it out for you because it's in 4 dimensions, R4. But the components are 2, 0, -5, and 5. And so we're going to square each of those components, add them up, and square root that. So here's our calculation right here. 2 squared is 4, 0 squared is going to give us 0. -5 squared gives us the 25, and +5 squared gives us also 25. So 4, 25, and 25 add up to 54. So this norm, or length, is the square root of 54. If we want to simplify that, we can rationalize it and pull out the 9. Remember, this is just square root of 9 times square root of 6. And so that's how we're getting the 3√6. Okay, so this brings us to the definition of a unit vector. So a unit vector is a vector whose length is 1. So in this case, the vector we just found is longer than 1. You could verify 3√6 is, of course, going to be a value longer than 1 when you convert that to decimal. So a unit vector is a vector whose length is 1. So in R2 and R3, alternate notation is sometimes used for these standard unit vectors. This is our familiar I, J, and K, maybe from physics class, or we saw it earlier in videos in chapter 4 as well. So I is 1, 0, and J is 0, 1. These are just our basis vectors, our standard basis vectors in R2. And then I, J, and K are our standard basis vectors in R3. I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. You can think about these as just being the vectors that are one long on each of the axes. And because they don't go out beyond their axis, the length on their axis, the 1 is just their norm. You can also, of course, put them in the formula and verify, oh yeah, 1 squared is 1. All the other 0 squareds aren't going to affect that. And then square root of the 1 is still 1. So we say two non-zero vectors, u and v, are going to be parallel when one of them is a scalar multiple of the other. So we can write that as u equals some scalar times v. In most cases, you're going to have to eyeball and look to see what the scalar multiple is yourself. You could graph them and verify if you're in 2 or 3 dimensions that they are scalar multiples. When we're in higher dimensions, you just kind of have to eyeball and say, you know, is one a scalar multiple of the other? You could divide if you like component-wise to figure out what that scalar is. So if C is a scalar that's positive, then u and v are going to be in the same direction. If C is a scalar that's negative, because we're taking u and multiplying it by a negative scalar, then we're going to say u and v have opposite directions. So theorem 5.1 is all about the length of a scalar multiple. So we're going to let v be a vector in Rn and C be a scalar. Then the norm of C, we're going to prove the norm of C times V is just the absolute value of C times the norm of V. So let's look at the proof. So we're going to let CV here be C multiplied through by each component, V1 through Vn. So then it follows when we do our norm formula here that we're going to have CV1 squared plus CV2 squared all the way through plus CVn squared. So we know we can factor out a C squared here. Everything's still in our square root of our V1 squared plus V2 squared plus so on, ending with our Vn squared, all still in our square root. And so then we know, well, we can just rewrite that as the square root of C squared times the square root of V1 squared plus V2 squared. And that's because in real numbers, you can factor inside roots. Be careful if you're doing these calculations in imaginary numbers, because these same properties don't actually hold for imaginary numbers. You'll see that if you take a class in what's known as complex analysis, where we take calculations like we're doing in this class and extend them to the field of complex numbers. So this holds for real numbers, but not necessarily for complex numbers. But we can factor out the square root of C squared. So that's just going to be the absolute value of C, because whatever C was, it's the positive version of that because we squared it and then square rooted. Multiplied by the square root of the V1 squared plus V2 squared, all the way through adding Vn squared, which is just the norm of V. So we end up right back here. So we have proved that the norm of a scalar times vector V is just the absolute value of that scalar times the norm of V. That's going to save you time when you are doing calculations by hand. All right, let's take a look at what the unit vector does in the direction of V. So if V is a non-zero vector in Rn, then the vector U equals V divided by the norm of V, has length 1. So when we divide by the norm, what we're doing is we're doing something called normalizing the vector to give it length 1. So you're either stretching or compressing the length of the vector to get that length to be 1. And it has the same direction as V. So U is called the unit vector in the direction of V. When we are calculating, we often say that we're normalizing V. Okay, so here's our proof. So we know that V is non-zero. So we know that the norm of V is not 0, because the only way we get 0 length or norm is for the 0 vector. You also know then, because the norm of V is going to be positive then, greater than 0, that 1 over V, 1 over the norm of V is positive. And so you can write u as a positive scalar multiple of v. You can say our scalar here is the 1 over the norm of v times v. Since it's scalar, it's going to be in the same direction. So it follows that u has the same direction of v, and then u has length 1 because you're multiplying here. If you do the norm of this vector u, you're multiplying 1 over the norm of v times the norm of v, which just gives you back out the 1. So this process of finding the unit vector in the direction of v is known as normalizing the vector v. And our next example shows this procedure. So let's find a unit vector in the direction of this given vector u, where u is 3 to negative 5, so using R3, three-dimensional space, in the direction opposite u. So we're going to have to put a negative in there, and then verify that u has length 1. Unit vector v in the direction of u, so same definition as before, I'm just flip-flopping what's my u and v here. I could have easily called the unit vector w or some other letter, so not to confuse you here, just flip-flopping u and v as generic vector terms. So normalizing our u is we're going to have 1 over the norm of u here, multiplied by each component of u. So you can verify the norm of u here is the square root of 38. So we're going to have 1 over the square root of 38 multiplied by our vector u. So when we normalize it, we usually write it with the roots on the bottom. I know that's not rationalized root form, so just be careful if you do any sort of calculations in SIMPy. It's going to rationalize the root for you because typically this is what we think of as bad notation in math, but we are tending to leave our calculations in this unrationalized form with the roots in the bottom when we normalize vectors. So here we've got 3 over root 38 for the first component, 2 over root 38 for the second component, and then negative 5 over root 38 for the third component. So we just took each component of vector u and divided it by the norm of u. And then the norm of this normalized vector should be 1, and you can verify 3 over root 38 squared plus 2 over root 38 squared plus negative 5 over root 38 squared. Well, if you just square the tops here, 9 plus 4 plus 28 gives us that 38. And then when we divide everything by 38, we get a 1, and square root of 1 is 1. So to get a unit vector in the opposite direction, we just put a negative on v. So you can see here we multiply the negative through, and so we get negative 3 over root 38 as the first component, negative 2 over root 38 is the second component, and 5 over root 38 is the third component. And then you can verify the norm of negative v, but when we square everything, we just get those same positive values. So we get the 9 plus 4 plus 25, which is 38 all over 38, which is 1. And so the square root of 1 gives us 1. So this is a normalized vector. So in the next video, I'll show you how to calculate the length or norm in SIMPy and do these kind of calculations with the help of technology.